Hello, thank you for the nice introduction. My name is Shrinath Kannan. I am a scientific researcher at the Technische University of Dresden, and I'm working in the electric power system and high voltage engineering department. And today's presentation will be about the impact of modern power electronic household equipment on harmonic resonance in residential low voltage networks. So the brief motivation is we are seeing an increased power electronic based equipment in the residential low voltage network, such as all the commercially available devices such as refrigerators, televisions, computers, and lamps. And also we have other utility applications such as the rooftop photovoltaic inverters, and of course, the very recent discussion on the electric vehicle chargers. So all these have a prominent capacitive behavior or predominantly capacitive behavior in the frequency range 100 Hertz or above the fundamental frequency till 2 kilohertz. And what they typically do is they interact with the distribution transformers impedance, which is the medium voltage / low voltage network transformer, and they produce harmonic resonances. So what you can see here is an image where we have shown measured network harmonic impedance from various public low voltage networks exclusively at the bus bar. And here you can see with respect to their exclusive extrapolated line, you see a deviation in the impedance profile. And because of this impedance, what really happens is, because of this higher magnitude, you have the prevailing harmonic disturbance levels getting amplified. So what we also know is these characteristics are very time dependent, meaning they are very dependent on the user behavior and other environmental conditions. For example, a rooftop PV, their characteristics are very much dependent on the irradiation level. So what it means is both the harmonics that is amplified by the resonance and the resonance are time dependent in nature. So this gives us the need or the objective that we need accurate models of these devices which are in residential low voltage network to analyze the resonance characteristics they affect and also the harmonics that they propagate. So what we see from the state of the art is these load models exclusively about the household devices. They do not represent two important things which are affecting the resonances. The first thing is that they do not adequately represent the time varying mixtures, that for any given instant in a household, we always have more than one device connected. That is, for example, a monitor, an LED lamp, and a refrigerator. All these are always connected in combinations at different points in a day. And also, there is no firm analysis on the impact of evolutionary impact on these mixtures. For example, in the past, we have different household devices which have exactly passive behavior, but these devices are increasingly replaced as power electronic devices. So whatever the variants, this first variant, we have a passive model, but they have fixed values and they are used for resonance analysis. And we have the second variant where we have a little bit of the variations in individual parameters, but albeit they do not exactly represent these two specificities for a given household model. So in this work, what we have done is we have tried to identify different time dependent and evolutionary mix of household equipment, which majorly aims to resolve the missing gaps from the state of the art. And once we have those models, what we will do is we will apply these load mixtures on a simulation network model, which is an urban network and a rural network, and we will try to analyze the impact of these household mixtures on resonances. So we begin with a modeling approach. As I mentioned before, in a given household, we will always have a simultaneous connection of many devices. So on the right, we have the probabilistic turn-on times of various household devices, which is from a thesis by Dr. Dickett at our institution. And these devices have a time-dependent behavior, which are classified into morning, noon, evening, and night. So this is the time slot, and these are the devices at which time they may probably may be turned on in a given household. What we also know is the load demand at the fundamental frequency also changes, albeit that's not the focus of the study. It's an important aspect to note down, because later we will also see how the increase in load demand at a fundamental frequency can be correlated with the change in the resonance characteristics. The device's operation point, apart from these probabilistic turn-on times, is also decided by two external factors. Two factors majorly. One external, which is the manual operation by the user. For example, a given user can always decide when to switch on and switch off a given device. And also the device may also decide its own internal operating point. For example, a PC, a personal computer, or a laptop, or a television may always decide to adjust its own operating point, for example, when the brightness changes. So when deciding a load mixture, these factors are always taken into account. And what is ensured is the load always remains at a constant operation point when we try to complete the further modeling approaches. So the second aspect is we discussed about the evolutionary impact of these household devices. So what we see is the device front end basically decides what kind of topology they have. So we have the non-power factor corrected, the passive, meaning we have a simple diode bridge rectifier as a front end in an LED lamp, for example. And this diode bridge rectifier, if they are supplemented with the input passive filter, so then it becomes a passive power factor corrected. Or if the entire device is made up of active switching devices, so then it becomes an active power factor or a stationary passive topology. So what we see here is, for example, the evolution-wise, the topologies have changed. For example, in this case, the incandescent lamps have been passive and they are non-existent in today's networks, that is in the present and the future. And we also have the CFL, which was non-existent in the past, but we have a non-PFC based CFL lamp, and it may be non-existent in the future. And an LED lamp, for example, non-existence in the past, but right now they are a non-power factor corrected or active power factor corrected, which is present as well as will be present in the future. So when deciding the load mixtures, these factors are taken into account. That's the evolutionary impact is also taken into account. And based on this, we have 9 different scenarios. It's important to note in the previous slide, we discussed about the load demand at the fundamental frequency. So these 9 load scenarios or the 9 mixtures is basically going to take care of the loading conditions at the fundamental, so the low, average, and peak. And also we have the evolutionary impact, the past, present, and the future. While deciding these load mixtures, what is also decided is the time dependency factor, which we have discussed before. So we have 9 different load scenarios, 3 for each, 3 for the evolutionary impact and 3 for the average or for the load demand. So the next step in the modeling approach is the load mixtures are recreated in the laboratory condition at our institute, Dresden. And these load mixtures input impedances are measured with an invasive impedance measurement equipment. And here on the right, we have 2 exemplary cases where we show the measured impedance curve and the fitted impedance curve using an RL parallel with RLC circuit. So here you see the load impedance curve is exhibiting a pure capacitive behavior until 2 kilohertz. And in this case, we see a resonant behavior even within the load mixture, and the fitted curve using this circuit is matching perfectly. So using these accurate load models, which are time dependent, also evolutionary dependent, and which have a combination of different varying load demands, is now then used for the simulation study. So we have 2 different networks, one with the urban network rated at 630 kVA with supplying about 180 customers, And then we have the rural network rated at 250 kVA, rated supplying about 30 users. For the preliminary study, what we have done here is we have took one load scenario and the equivalent RLC parameters are applied to all the customers in the network. So meaning this is a little bit of an idealistic scenario. Not every household, not every phase will use the same load mixture. But to begin with, since we want to analyze the resonance characteristics, we are starting there. What we then do is we use the ratio, the magnitude ratio between the actual and extrapolated impedance to identify and quantify the resonances. So the figure on the right here, you can see the black line in both the curves is the extrapolated line. And we have the 9 different scenarios for the past, present, and the future, and for the different loading conditions in this case. So what we can see here is the no resonance scenario, which is represented by the solid lines, are definitely, there are no resonance conditions in the past scenario. So meaning what we hypothesize that in the past, since the devices are passive, we are not seeing any resonance conditions at all. But however, for the futuristic and the present scenario, which are represented by the dot and the dashed line in the both urban and rural network, we are seeing a very high probability of the presence of resonances in this frequency range. So then we would like to quantify these resonances, their amplifications, as well as the frequency a little bit in detail. So then we see in this table the common properties for both urban and rural network. So as I mentioned before, the present and future scenarios have equal likelihood for resonances. The low and medium loading conditions, they yield a very strong resonance intensity, so which is marked here. So in this case, we have a stronger intensity for the low, and then it's also reasonably intense for the medium loading conditions as well. What we also see for both these urban and rural cases, as marked with this arrow, is when the loading conditions increases, the resonant frequency and the intensity decreases. This is what all these load mixtures constitute are nothing but parallelotronic devices. So on to the contrary opinion that addition of more parallelotronic devices may cause higher resonance is not actually true. So higher the parallelotronic devices, higher the loading conditions, higher the damping that we get, and lower the resonance frequency as well as the intensity. So then between the urban and rural network, what we see is we have a lower resonance frequency and a higher resonance intensity in the urban network. For example, let's take in the low loading condition, we have of this case, and we have rural, we have a lower intensity and higher resonance condition. What is the reason for this is we have a higher number of customer, and the cable impedances in the urban network does influence the resonance characteristics more. So the resistive property of the cables in this urban network is providing or causing the resonances to be lower. So finally, we would also like to see how this fares, how the simulation results fares with the field measurement results. So the time-dependent characteristics of resonances shown in this figure. So this was measured at the point of connection at a household in a residential low voltage network. What we can see is the resonant magnitude is highest when at the night. So the October 3rd here marks the midnight, and the resonance is actually highest, which is in correlation with our simulation results. And when the load demand increases from the night to day, we see the resonant frequency coming down, which is also inconsistent with the simulation results. So this is it is much consistent for from the experimental results, as this phenomena is observed for both for 2 days continuously. So what we can really conclude is what we have observed in the simulation results is much consistent with the field measurement results as well. So to summarize, we have the frequency domain impedance models for household mixtures, which are representing the time-dependent and evolutionary stages. What we see is the likelihood of resonances increases in the present and future scenarios. The urban networks are prone to slightly severe resonance compared to rural networks. So for the network operators, this might be of special interest in analyzing resonances in the network. So for the future works, we will do more load mixtures or recreate more load mixtures in the lab and try to measure and derive the input impedances, which makes sure the model that we use for analyzing resonances are more accurate. So the resonance analysis is also more accurate. Then we would also like to do more impedance measurement campaigns to validate the simulation results, especially on the long time measurements at a given point of connection in a network. So that's it from my side, and thank you for your attention, and I'm open for questions.